I actually won't talk about this. This is what my original talk was all about. Then on Saturday, I saw the program and saw that Charles Falco had spoken about this optical projection theory. So I thought it was a great opportunity to also present on exactly that topic. I'll have to go fast, but I assure you that everything I would have talked about and everything I will talk about is thoroughly documented here in Pixels and Paintings, Foundations of Computer-Assisted Connoisseurship, which just came out, 784 pages, 600 citations, so it's fully cited with scholarly consensus. So you saw that there are claims that Jan van Eyck used some sort of optical projection during the execution of this Arnolfini portrait in the National Gallery in Trafalgar Square. And Hockney and Falco claimed that the convex mirror depicted within the painting could have been used as a projection mirror. They said Van Eyck placed a convex mirror at the very center of this Arnolfini masterpiece. The very mirror which turned around he may well have used to construct this image. I thought I'd test it. And one way to check that is to look at the focal length of this mirror, had it been used, and the focal length that would have been needed to produce that image. I won't go through the mathematics. It's actually very simple. I teach my undergraduate art history majors at Stanford how to do this. If you know the sizes of objects, standing people, beds, and so forth, and you have a projection, you can find where the center of projection is, basically how far away the lens or the artist's eye would be. But to do that, you need to have consistent sets of assumptions about the objects. So we made an independent person, made a 3D computer graphics model. There are, of course, going to be uncertainties, but that's not going to lead to any bias. We don't know if they're a little too high, tall, too small, a little close, and so forth. It'll add uncertainty, which we calculate, but it doesn't add bias. And so here's a view from the side of Arnolfini, his wife, the chandelier, and so forth. And I'm showing it with a lens just because it's easier to show here, but the lens equation is the same as the concave mirror equation, so the mathematics is identical. And if you have the size of the image, and this is the painting to scale, has to be inverted, that the size of the image of the chandelier corresponds to the size of the real chandelier. Of course, it's not real, it's computer graphics. Size of Arnolfini, and so forth, 13 pairs of objects and images. And once you have this set up, you have the object distance from an object to the lens, and the image distance from the image to the lens. It's high school optics. You calculate the focal length. Turns out to be 61 plus or minus 8 centimeters. Well, now let's find the focal length of the convex mirror. Antonio Cremonese first applied this to this painting, and I've redid it, but here's the cap of a convex mirror. I won't go through all the optics, but there's a transformation between positions within the mirror and the positions out in the field of view that depends upon R, the radius of curvature. How bulgy is the mirror? And we don't know what it is offhand. So in computer software, we can easily adjust that radius of curvature until the de-warped image is as rectilinear as possible, because we can certainly believe that the doorways were vertical and the windows and so forth. And when you do that, the optimal image you get is this. And you notice that the window is nice and rectilinear and so forth. And we see the back of Arnolfini, the back of his wife, the two witnesses to the wedding coming through. But now we have an estimate of the curvature, the radius of curvature of the mirror, and the focal length would be 1/2 that distance. And so here is what I just showed you. And if Hockney and Falco are correct, that this mirror could have been used as a projection mirror, this focal length should be pretty close to this. But when you do the math, 18 plus or minus 4 centimeters, much, much, much too short, simply couldn't have been done. And here from my Scientific American article is a way to visualize how that mirror could not have been done, used as a projection mirror. Here's the sphere that has the proper radius for that 61 centimeters. That radius of curvature would be twice that. Here would be a putative projection mirror drawn large just so we can see it. And here's the sphere for the back. Simply, positively could not have been done. But it's worse than that, because if you have a perfect section of a sphere, its image is terrible. It has what's called a blur spot, and if you go through computer ray tracing, you find it's 9 millimeters across. So you wouldn't get an image nice and sharp like this that you could trace over and get all the nice details. No, it would look like this. But it's much worse than that, because you would never get a section of a perfect sphere. These were hand-blown glass spheres with undulations and so forth. And so if you add even just the slightest amount of imperfections in here, the blur spot jumps to a whopping 2.5 centimeters. So this is the quality of the image you would get using the mirror that Hockney and Falco claim could have been used for a projection mirror. I'm going to come back to the issue of off-axis aberrations. If you actually set up the system, you have to do it off-axis, and that gives it even worse. But it's even worse than that for the theory, because these mirrors at the time were blown from spheres of glass. They would put tin and mercury in them, cut them out, and then put tar on the back sides to keep it from tarnishing and so forth. So we could not have projected an image whatsoever.
Which is why we didn't say that.
You said, but so now you agree that this couldn't have been done.
For 25 years, we've said that.
Oh, great. We'll talk about this. So might a different mirror have been used? Well, no, because if you look at parallel straight lines here, they don't meet at any vanishing point. Straight lines here meet at a vanishing point here. This one doesn't. They said, oh, well, maybe he did a little patch here with one mirror and then moved it around and so forth. That can't allow you to get the straight lines, anything like this. So
yeah, it's not a photograph.
It's not a photograph. They didn't have this projection here.
No, the whole picture is not a photograph.
So it's
individual elements.
And if you want to do individual elements here and get things in proper perspective, how do you make sure that it's going to be perfectly straight lines during all these things in order to get to these points? I ask you to hold those questions. Please bring the questions at the end so we can do them justice. Hockney said, quote, "That chandelier is in perfect perspective." He told 8 million people on CBS 60 Minutes that the chandelier is in perfect perspective, and certainly looks pretty impressive, but I thought I'd check. Here is the overhead view or plan of the 6-arm chandelier. Consider 2 points, corresponding points on 2 arms. Think of my 2 arms as chandelier arms. Think of my thumb and this thumb. That defines a line in this room. That line is parallel to the floor and perpendicular to the vertical plane bisecting these 2 arms. So that line is parallel to the floor. Think of the 2 elbows as other points on the chandelier arms. Those define a line in this room, also parallel to the floor and perpendicular to the vertical plane bisecting these 2 arms. So those 2 lines are parallel in Arnolfini's room, like this. Also, other pairs of points on those 2 arms. And so this is what I've just shown you, the parallel lines on these 2 arms. And if you think about symmetry, lines defined by these 2 arms are parallel. And if you really think about symmetry, lines defined by corresponding points on these 2 arms are also parallel. They're all parallel. So here's a symmetric computer graphics model of the chandelier. And if these are parallel lines and there's a projection, as they claim, as Hockney claims, he demonstrates on CBS 60 Minutes, they actually make a projection and he traces the arms and the crockets and so forth. If we do a projection, these lines should, when extended, meet at a vanishing point. And sure enough, they do. Here is the Arnolfini chandelier. Hockney says it's, quote, in perfect perspective. So if we do the same kind of extension of these sight lines, we better get a vanishing point somewhere down here. But when you try it, here's what you get. Kaboom. A mess. Absolutely a mess. Not close to being proper perspective, not even close. Here's a close-up just so I can show you a straight line like this, extended, straight line like this, extended, straight line like this, extended, so forth, and a few others, and the same thing happens on these other ones, and so forth. If any of you teach a course on this material, this is a really great homework problem. My undergraduates then draw these lines and say, oh my goodness, you know, it's really not in proper perspective at all. One student came up to me afterwards and said, but I love Hockney's paintings. So you should learn that you go by the science, not how famous the artist is. The proper way to do this, the principled way, is not to use Adobe Illustrator and grab something and map one arm onto the other. Use a technique developed by Antonio Cremonese, who won the ACM Dissertation Award with the work that I'm just about to show you. He got his PhD in computer science here at Cambridge. If you have shapes that are not commensurate, you can always do what's called a homography, basically map one arm onto the other. If they're of the different shapes, you can always get one that'll get the elbows to overlap, but then the hands don't. Or you can get another one to get the hands overlap, but now the elbows don't. But what is the best overall alignment? And he did this in his dissertation, and when you apply that to the chandelier arms, you get this whopping discrepancy, 8 to 10 centimeters in the chandelier in Arnolfini's room. Much, much, much too large to be consistent with Hockney's claim. After I came out with this, Charles Falco said, oh, well, these were hand soldered. You can tell me whether that's wrong, but I can get you the quote about the soldering. These were never soldered at the time. This is so-called denandry, and these arms were all made from the same mold. They have the exact same shape, and then they're aligned around the corner, so around the vertical axis. So the claim that they're goofy and poorly shaped because of soldering is simply false. And they are also highly, highly symmetric. Not only has Antonio Cremonese and I worked on photographs, doing photogrammetry on collections of denandry, but I've gone out to museums with a tape measure and measured them. They're symmetric to within 1 millimeter, not this whopping 10 centimeter difference. There is one part of the Arnolfini chandelier that's in reasonable perspective. The tips of the candle holders, if you do a homography of a perfect hexagon, it meets it pretty well. This is all a mess. All of this is a mess that I've already shown you, but this is reasonably good. Well, do you need optics to do this, to get anything in even this moderately accurate portion of the chandelier arm? No. As part of our research, we had a realist artist paint 2 chandeliers entirely by eye, no projections, no even rulers and things like this. Nicholas Williams here in England. Here's a 5-arm chandelier. You do a pentagon, and it matches as well, in fact, slightly better than the Arnolfini chandelier. And here's this really lovely chandelier, 2 very ornate. You can't tell whether it's in proper perspective. I can't either. It's hanging over my bed at home. But now we can use Cremonese's method. So here's one of those arms segmented out. Here's another arm segmented out. And you do a homography. You transform this to be as similar to this using basically like a perspective transform. And that's what you get here. Ignore the fact that the pan balance comes out beyond. The homography goes from one plane to another plane. Things that stick out aren't properly transformed. And so now we can overlap this with this to see how well they coincide, and they coincide incredibly well, down to about 1 millimeter in the painting. So you don't need optics in order to get this kind of accuracy. The first painting that was used in this theory is Lorenzo Lotto's husband and wife in the Hermitage Museum. Apparently Falco gave you an explanation of some of this on Tuesday. I'll just give you a touch of it. I'm happy to go through much more detail if you'd like. If you do a perspective analysis of the front part of the carpet, you see these lines go in one direction, but if you go further back, they go in a different direction, and there's a slight scale difference and so forth. How to explain that? Well, they claim that Lorenzo Lotto, without any documentary evidence that he did anything like this, built a concave mirror projector, projected the front part of the carpet, traced it, but there'd be depth of field problems, a range of distances beyond which the carpet would be blurry or out of focus, and that he would reposition the concave mirror in order to focus on the back part, and that could indeed change the magnification, also the position of the vanishing points. Well, and there's more, but this is enough for my analyses. Here's from the Hockney-Falco paper, the setup that they claim. So here's the table where the subject is. This is the object distance, and they use the term mirror lens. It's just a concave mirror, and that it would project an upside-down image here. The reason they prefer the concave mirror rather than a lens is because it preserves the parity, the left-right reverse status, and so they've been using that primarily throughout their explanations. I won't go through a recent paper where the mathematics is here that describes Falco's description of the change in the magnification and depth of field and so forth, but it's all here. You can read about it in my book. I have exactly these things where you have a so-called circle of confusion and simple mathematics that tells you depth of field and depth of focus, all sort of freshman level optics. But there's a problem with this projector. It's all set up here, and I claim that this projector cannot work as it's set up here. Simply cannot work. Why? Well, where's the canvas? That if you put in the 116 centimeter wide canvas, it blocks the light from the table that would strike the mirror and then come to the canvas that Lotto would trace and so forth. So here is the unrealistic projector that's exactly taken the numbers from the Hockney and Falco paper, but within the unrealistic, I'll call it impossible, projector system, where you have the table, the concave mirror, and the projected image, or the canvas here. And as they properly state, if you look at the image, this is ZMAX computer ray tracing software. Indeed, if you focus on the front part, it's nice and sharp. You'd be able to see a nice image, but further back, it'd be really blurry. This is consistent with everything that they said in their paper, everything except the fact that they didn't include the canvas in the projector. When you now make a realistic, let me go back. When you now make a realistic case where the canvas is off to the side, as it must be, if you're going to get light from the table to the concave mirror to the canvas, you have now what are called off-axis aberrations. You don't get this difference in the nice sharp point and something distant. And here is, again, computer ray tracing, getting the sharpest image you can under this setup. First of all, the blur spots are very large, much larger. And you can easily demonstrate this if you have a concave shaving or makeup mirror, put a line in and focus it straight on. Oh, nice and sharp. And now start tipping it off. And oh my goodness, it gets very, very blurry, just as you see here. Moreover, the blur spots for the distant are just as large. So first of all, it's too blurry for you to get a good enough image, just as we saw with the Arnolfini chandelier. But the fundamental process of depth of field limitations would never have occurred once you use the realistic projector that the canvas must be in this setup. Christopher Tyler had pointed out that, oh, well, even if Lotto did do a projection here, then this should be in proper perspective. The parallel lines here should all meet at a vanishing point and so forth. They do not. Look at the front part of the canvas of the carpet. No refocusing here, but this part of the line, this yellow section, should line up with this one. It doesn't. Top of this crenellated pattern should line up with this one. It doesn't. There are a whole host of perspective anomalies in here that cannot be attributed to the use of optics because they're within a single putative focus or exposure is perhaps a better term. I've looked at other carpets. They're called Lotto carpets, made in the Uşak region in present-day Turkey. This is, again, a Lorenzo Lotto. They're the same distance away. No refocusing here, and the asymmetry in the carpet is so large and cannot be attributed to optics. Here's the yellow line going from this corner here to the middle of this. If you flip it by the axis of symmetry, it would be over here, like this. But in fact, it's in this purple. This one's too low and too short. This one's too high, and so forth. Just asymmetric and cannot be explained due to optics. And then we've looked at carpets surviving in museum collections. They are asymmetric. They are asymmetric. Here's one from the from the Metropolitan Museum in New York, another Uşak Lotto carpet. Here's the axis of symmetry. You trace one half of it, you get this, and you flip it to the other side, and here you are, you get enormous differences, a factor of 10 larger than the kinds of fits that Hockney and Falco use. They fit the data to three significant figures, and the carpets are asymmetric to at least an order of magnitude larger.
Or an image or painting?
This is a photograph of a carpet surviving in museum collections. At home we have 36 carpets, including a Lotto carpet, and I've gotten out and measured that one. That also is asymmetric in a way. Please hold questions and we'll get them at the end. And the last painting I have time to go through is Georges Villatour's Christ in the Carpenter's Studio. In Hockney's book, Secret Knowledge, he says, the source of light seems to be outside the picture, as it must be if you use optics. Joseph and the girl, it's not a girl, it's Christ, were probably painted separately, each lit by a shielded light source in place of the other figure. And in his book, he shows two, I'll call them half paintings. What he says, when Christ was painted, the light source was in place of St. Joseph. And when St. Joseph was painted, the light source was in place of Christ. So you have to look at this, or outside the picture. You have to look at this and say, where's the light source? Humans are really bad at it. Even famous painters are really bad at it, as I'm going to show you in just a moment. But computer methods are better than humans for lighting, and it's been tested on photographs using techniques from Hani Farid at UC Berkeley. So the simplest method to find the location of the illumination is to use cast shadow analysis. So you take a point on an occluder like St. Joseph's left thumb, its corresponding cast shadow point, and draw a straight line through it, and bingo, straight to the candle. Not in place of Christ, and certainly not outside the canvas, as Hockney claims. If you do a full set of these, you get these cast shadows. And indeed, there's one that is with a very small moment arm that is somewhat consistent here, certainly not outside here, but the vast majority meet right at the candle. And you see these contours of, these gray contours. These are contours of likelihood estimation. Given all this evidence, and we have to decide where the light source is, well, we use maximum likelihood estimation. Basically, that each cast shadow tells you a given direction with a given fall off. You multiply those probabilities, most likely here, less likely here, less likely here. That's what I have here. Certainly at the candle, not outside the frame of the painting, as Hockney claimed. Then we use a very sophisticated technique that's been developed for forensic photography, trying to find lighting inconsistencies in photographs, and applied it to the painting. I'd love to talk to you about how it works, but basically you get a contour here. You choose a contour that has uniform albedo, inherent reflectivity, is it white or gray or black, And the computer measures the lightness along that contour, and based on that, finds the direction of the illumination. And you put all these together, and bingo, they really meet very closely to the candle. Certainly not outside the frame of the painting, as Hockney says. And I find this really quite amazing, that the computer can look at the pattern of light across Christ's chin and say, you know, the lighting direction is here. So all these red lines were put in by the computer, not us, and they meet at the candle. And you can do the same maximum likelihood estimation on this, and putting all this evidence together, bingo, right at the candle, less likely here, less likely here, less likely here. And one of the benefits of using probability is now we can put together more and more evidence. So here's the cast shadow evidence I told you, here's the occluding contour evidence I showed you, and to put them both together, you basically just multiply those probabilities. And bingo, very close to the candle, not in place of the other figures, and not outside. But there's more lighting information that we have not yet used. Look at the pattern of light over the floor. It's bright in the middle, dark on the sides. Where would there be a light source that would lead to something like this? Would it be over here? Would it be over here? No, it's going to be somewhere in the middle. I won't go through all the mathematics, but you can make a physical model of the so-called appearance model in computer graphics and say how the pattern of light on the floor depends based on a particular location. Then you work backwards and then do gradient descent to solve where it must be. And when you do that, it turns out to be here. Now, it's not exactly at the candle, but it's certainly not in place of the other figure, and it's certainly not outside. And we've done this on each half, doing it just for St. Joseph, just for Christ. And the reason grad student and I figured out is that why it's probably a little bit low is that the albedo range for paint is only about a factor of 100. The whitest white you can get is only about a factor of 100 brighter than the darkest black, whereas the range of lightness in actual figures is much larger, maybe 10,000, maybe 100,000. But as far as the claim is concerned, Hockney's claim is concerned, we can reject that. But there's yet other lighting information that we have not yet used. The pattern of light over Christ's chest, over St. Joseph's chest, and so forth. And to capture that, we build a 3D computer graphics model without referring to the light. We just get the shape here, and it was a scholar, not me, another scholar, a Japanese scholar, not me, who created this computer graphics model. And here is, just so you can see it, you see the tools like this, and St. Joseph the Carpenter, Christ is the light of the world. I hope you can see the shadow changing down here as we change the position of the virtual light in the tableau. And then we're going to stop the configuration and rotate around, look at it from the back so that we can see it from every possible direction. We're going to stop it in the configuration that matches the actual painting and do what's called an alpha blend to go all the way to the actual painting, which matches really closely. And now we can test Hockney's claim the following way. We're going to put a light source, virtual light source in the tableau in place of St. Joseph and then illuminate Christ. And then we're going to put a light source in place of the candle and then illuminate Christ and see which one matches the painting best. Well, the problem is we don't know the depth into the painting, into the tableau, which we should do. So we tried 19 positions with the light source in place of St. Joseph and chose the best. Chose 19 positions, the light source in place of the candle, chose the best, and then rendered Christ. And here is the best image we could get with the light source in place of St. Joseph. This is what it looks like. And here is the light source in place of the candle. And we have to say which one of those two models, the Hockney model or the non-Hockney, the candle model, matches the painting best. And there's no question that it's in place of the candle. Look at the pattern of light over Christ's chest. Look at the direction of the cast shadow of the shin. It's not exactly the same. This is a painting after all. But over here, it's much, much different. So there's no question that the light was in place of the candle, and Hockney's wrong. I don't have time to go through these paintings. I would love to, if anyone has seen these things and said, oh, I was really convinced about the Albergati portrait, please ask, and I'll tell you, or any of these, and I'm happy to give explanations, rebuttals on those works as well. So that's my beginning. Now to my talk. This is what I really wanted to talk about for a scale conference. Let me start with pose in portraits. It's a really important formal property of a portrait, the angles and so forth. And up to now, art scholars have looked at or have been doing this kind of analysis entirely by eye. They say, oh, this person's in a portrait in a profile view, 3/4 and so forth. But if you wanted to change the scale and look at thousands or tens of thousands of portraits in order to test the, to look at trends and so forth, you couldn't do it by eye. It just takes much too long. So, grad student Stanford and I built some computer code that will do it on large scale data sets. So we're going to describe the portrait pose using 3 angles. If you're a pilot, you know what yaw, roll, and pitch are. And then we used deep networks, and then the I'll call it the projection model, or the, which is not an optical projection, basically the artist's model is to have a picture plane here in the center of projection and have points here, and it's the location of these points that one can use to infer those three angles. I won't go through the deep networks that we used, perspective and point, and the fine-grained structured aggregation network. If there are AI people here who want details, please ask me at the end. But we can now apply this to paintings and get yaw, in this case, yaw estimations, even on paintings like Modigliani and so forth. And we can also get bounding boxes, which we used for another study. But here are the kind of results you get when you apply to, I think it was 12,000 or 10,000 paintings grouped by different art movements. So here's ukiyo-e and naive art. Notice so these are box whisker diagrams, what roll angles of the portrait you get. Much, much larger for ukiyo-e than naive primitivism, and it pops out right out of the data like this. And so if you're familiar with Japanese ukiyo-e, woodblock prints, hokusai and so forth, you know that there are often key moments in kabuki plays called mie poses. So during the performance, the actor will stop and make a very dramatic pose. And so forth. So they're all tipped at many, many different angles, and also the geishas are very often in very seductive poses and so forth. Whereas in primitive, so-called primitive art, these are often untrained artists, so they're much more vertical and so forth. Just as we saw, even brilliant draftsmen like Matisse would sometimes try to be, or deliberately somewhat childlike, so to speak, and have it simple and vertical. And so that we get that kind of data straight out at a scale that non-computer connoisseurs simply can't get. Then we came across several surprising results. If you think about a self-portraitist, a right-handed self-portraitist will stand one way, a left-handed self-portraitist will stand the other way, and so their tip angles will be different. We can find left-handed people, left-handed self-portraitists in a database of 20,212 paintings. The computer pops them out, and then we go and check. Sometimes there's documentary evidence that they're left-handed, and other times you can tell from independent paintings whether or not they were right or left-handed. We've also extended this to add gender to it. We use deep neural networks to tell whether there's going to be difference with men and women over time and so forth. I don't have time to do the analysis, but I want you to show I want to show you the kind of tools that my book describes. Then there's issues of looking at trends in landscape paintings. And to understand that, we need a principled way for splitting and breaking up an image. And I won't go through, it's very basic information theory, conditional entropy. Basically, you quantize the pixels into n colors and look at the diversity using conditional entropy. So these has no uncertainty. Once you got blue, it's all through. Likewise, this is going to be higher, and this is going to be higher still. And you can use, so let's take Van Gogh's painting here, Harvest. So we do this analysis. We pixelate it here, or we break it into pixels, and not only larger blocks, but also color quantize it. And now the computer basically samples possible cuts through different layers. If you cut it here, what will be the entropy of this plus the entropy of this, and so forth. If you cut it right here, where the peak is, it basically peels off the purest part here. So this is one way to find where the horizon line is. But we're interested in more subtle portions and apportionments of the design. And so this work started with Lee, it's also in my book, but so if you use that information theoretic method, you can find the horizon line like this. This is the single cut that will reduce that entropy as much as possible. If you now do the second cut, you're always allowed to do either the horizontal or the vertical on any given portion here. So you do something like this, it goes up like this. That's after 2. I'll jump to 5 and jump to 10. And it's a way of splitting the image. And now we can do statistics where what's the height of the horizon line, how complex is it, how often is it split vertically, and there are all these statistical methods you can do. And if you were just analyzing one single painting, this would be a little bit coarse, that you wouldn't, maybe you'd be more detailed about something like this. But if you want to do 10,000 paintings and look at the trends, how did the horizon line change throughout Western art and so forth, you'd use a computer method like this. And the kinds of results you get are things like this. This is during different periods, 1510, 1530, all the way up to 1990, or different movements and different individual artists and so forth. This is a particular measure of the complexity of the final divisions of the image.
What are the colors? Brown.
Oh, that's just to keep them separate so that it's easier to see that this is a different one than this. The color here means nothing, really. And then once I saw that the cover of this conference had a Mondrian on it, we've also published several papers on learning the design principles in Mondrian. Here, computer renderings of about 1/3 of the paintings that we used in training. We use a hidden Markov model that basically, first of all, learns the aspect ratio and sets an aspect ratio. Is the painting going to be like this? It's going to be like this, and so forth. Then it goes to either draw a horizontal line or a vertical line, and you have distributions over where you're going to place it. You go back and forth several times. Then you go to something that's going to set color, and then do that several times, all statistically, and they come to the end. No one for a moment is trying to say that this is how Mondrian did his composition. Oh, I'm first going to do this, and then only do, no. But the question is this a rich enough model in order to model what he, in fact, does do? And we've produced these, and then you show them to art scholars who know Mondrian, and invariably they say, that's not a Mondrian, because they know every Mondrian. There aren't that many, and they've seen them all. Nevertheless, they can subjectively judge that this one is really pretty good, and so forth. It also can be used in a recognition mode, and you can use this network to classify a painting. Is it a genuine Mondrian? Yes or no. And I have plenty more to talk about. Unfortunately, I don't have time. Again, you can find all the information on it in this book that was just published. If you happen to be at Stanford next Thursday, we're having a book release party in the art library. please come. Thanks very much. Charles, of course.
Okay, so the de la Tour and the concave mirror in the Arnolfini marriage are total red herrings, as we've written about 25 years ago, that we've also written that we cannot distinguish in any painting between whether a lens was used or a concave mirror was used, and because there's no way to tell. The audience has seen, we've reproduced the Lotto painting, basically, optically, as we have every optical thing we've done, we've reproduced experimentally. The de la Tour painting is an offhand comment, if you will, that David made in a book on painting that's got nothing to do with optics. It's got nothing to do with whether or not optics was used. We said that the Arnolfini chandelier is in perfect perspective. It is in perfect perspective, but it's an imperfect chandelier, and we've also shown that. So I'd encourage anybody to, you can go to my webpage, download PDFs of all of our papers, critically read everything, all of our assumptions, you critically read them, decide for yourself whether the assumption makes sense, is justifiable, and read our conclusions, and do the same with David Stork's papers. Please
do. And I also urge you to look at, let's see, where is it? So here's a list of independent scholars who have rebutted the Hockney-Falco theory. There was an entire workshop, 4-day workshop in Europe. I didn't attend, 4-day workshop that was presented all the arguments and unanimously rejected the claim.
That's not true.
I'm happy to give you the quote from, here's the editor of it. The Hockney-Falco thesis is extremely unlikely as far as its application for the period before the first textual reference to image projection around 1550. So
that was Sven's conclusion himself.
I'm sorry?
That was Sven's conclusion.
No, he's the editor of the journal and wrote the summary paper. I've also looked at every other paper, and if you'd like to see the quotes, I have the quotes on those in my review of this book in Nature magazine. I go through each one of the chapters that rebuts it one after another. Do a quick search. Can we do a quick search here?
I'd rather us stick to the particular questions which are pertinent to this meeting, if we might.
Let's move on to something else. This will get nowhere.
Yeah, I think that would be preferable as far as I'm concerned.
Me too.
Okay,
Yeah.
please. Yeah.
I guess I have
So as far as I can see, you do agree that
Don't tell me what I agree.
Okay, all right.
So-
Well, I'll see if anyone else agrees that the projection diagram from their first paper, which, by the way, was not peer-reviewed. It was in a non-peer-reviewed journal, Optics and Photonics News. I think any journal that had a peer review would have seen that that projector simply couldn't work. Yeah.
So I guess I'm not making any judgments here. I'm all
Go ahead.
sides of the arguments, but so in the carpet example where you
Yeah.
put the one from the museum, I mean, you said you had this analysis. It wasn't or it was symmetrical. So here, I mean, looking at that one, is this analysis what you're showing on this slide, or is this just you drawing in the lines by hand on PowerPoint?
I drew this by looking through the center of this and the center of this. You can change that a little bit. There's no question that this is not symmetric. To at least an order of magnitude larger.
This just looks like it's a hand.
Look at the straight line along the bottom. Do you believe that's a straight line? Yes or no?
I mean, I'm just looking at the yellow line, and it doesn't line up with.
Goes right through this and here. Even if I okay, I can easily change that. I urge you to do it. Just do a search on Lotto Carpet, Metropolitan Museum of Art. You'll find this. Do your own, please. Yeah.
How was the photograph taken?
Yeah.
Perfect. First of all, that won't change the symmetry, even if it's, but it's centered. The full, I can go search on it and show you. You see the full carpet, and we're just pulling down the individual one.
Is the full photograph of the Met published?
I'm sorry?
Is the full photographs of the Met published?
Yes, yes, we just download them from the web.
The only reason I think that raises working inside a museum, I know how manipulated our photographs even are to get full images of carpets and something as large as a carpet.
Again,
itself might be stitched together from multiple photographs.
oh, no. We've gone to, as I say, we have them in homes, we've measured them directly, and you would have to prove that that particular one was symmetric to three significant figures. Do you really believe that? By the way, these were made by two young girls at the same time on a big loom, taking several months. You take them down from the frame, the stresses are going to be relieved, you roll them up and put them on donkey carts.
You never said they were symmetric.
That
Doesn't,
this is much larger than any of the changes in the magnification, and
that's not true either.
So,
yes, it is.
should we move on from this? I
Other
think we all
questions?
agree that there's discrepancy in
I
carpets.
refer to the painting basis for that discussion, but a different aspect. You told us that if it was not projected through a lens but through a mirror, the canvas would block the view if you choose the best angle. Now, that's my personal view.
Yeah.
Imagine, I don't know in which order he painted that, but imagine he had finished the man, the lady, and something else.
Yeah.
So the picture is already, he worked on that days and weeks and months, so it has already its value. Now to the details where I don't need the people to sit for the portrait. Why should he do this tinkering of this carpet on the huge canvas? This is when I finish
That's
an
their
artwork
theory.
to 80%. Why should I damage it by doing this lineups? So I would think, or maybe you would like to really think that if he could, just in theory, use a smaller, like I don't know, material, let's say paper or a piece of wood, because I know
First of all,
large
that's most
paintings
certainly
like
not
on
their
walls,
claim.
or they had templates, they had what's the word?
And what's your evidence for
Stencils.
that they
So
did it on this painting?
Just a question. So, if they could do a kind of a small size template in the better angle, which doesn't block the view, so you can move it more to the counterclockwise position, and the small image.
Okay, that's
Just the decoration would not block the perfect point.
so that's
of-
the kind of explanation you keep getting forced into again and again. All right, well, here's a diagram. It doesn't work, but the only way you can do it is do it on paper and then transfer it.
Can we move on to the second part of the talk?
Yeah,
Is
the
that
second
one?
part.
Yeah, I was going to try to move on. Could you
Good.
tell us like some of the most exciting
Maybe.
results that the machine learning statistical analyses tell us? Just in your, like as an advertisement for your book and your work, what are
Sure.
some of the
Well, I think
cool
there's some
findings?
really interesting work being done on attribution, doing image-based attribution, and the work I'm doing now, which is into my next book, which I'm working on, is on image-based authentication plus putting together textual provenance and material studies. How do you reason? It turns out there are so many fakes and misattributed works, and if you put together the information optimally, you can do much, much better. So I think the 20% of artworks that are on museum walls that are fake or misattributed will change in part due to these kinds of methods. Yeah.
So, with all these AI methods that are you using, do you consider also going into generative AI and
Yes, one of the problems we're working on now.
This Mondrian example is somewhat
Yeah, we're working, several students and I are working on recovering images of lost paintings. Some of the most important artworks that were ever created were lost in fire, flood, vandalism, and so forth. But we have preparatory sketches. We have copies by other artists. We have surviving works by this artist. We have textual descriptions of them. And can you put all that together to get an approximated image of the lost artwork? And we have a few proof of concepts, but it takes a lot of training and a lot of curation of the data in order to get that. So I think that could revolutionize art history. Art history is driven by what works happen to survive, not what works that were really important. So for instance, tell me when I should go, but the famous Las Meninas by Velázquez was saved in a fire in the Alcazar Palace in Christmas Eve, 1743. But the expulsion of the Moriscos, which contemporary people thought was even better, burned. And if we could recover that, it would be really interesting to see what art scholars make of that painting. Anyway, thank you very much.
Thanks very much.